Okay, so it says use the graph to determine the average acceleration during the final 2 milliseconds of the graph. Okay, so let's go back. We got to look at the graph to do this. We're going to find the average acceleration during the final 2 milliseconds, right? So that is like here, right? It's like there to here, right? Okay. So what I'm going to do, I want to find the average force. I think that's going to be about the average force. Now notice that it's dividing 500 into 10 parts, right? So every square is 50 newtons, right? So now to read the graph, it's going to be, what is that, 50, 2000, 2050, 21, 2100, 2125. I'm going to say that the average force is 2125 newtons, right? So just read that as carefully as you can. I actually use my calculator because I'm really bad at reading graphs, and they tend to give you graph scales. So what I do with my calculator is I go 22,000, right? Because we're above 2,000 by 2.5 squares. So plus 2.5 times 50, right? So just try that, 2,000 plus 2.5 times 50. Maybe you're better at just sort of like reading that that's the number, but that's our average force. And then the average acceleration is going to be force divided by mass. Here's your mass, right? So the mass is 0.032. That's your force. Plug it in. It's a big number, okay? I got a number between 60,000 and 70,000, okay? So that's the average acceleration, right? Okay. Then it says, show that the change in momentum of the bullet as the bullet travels along the length of the barrel is approximately 9 newton seconds. Well, 9 newton seconds, we got to find the area under this graph, right? Okay, so this is going to be an enormous pain, okay? We want to find the area under this thing, right? Because this is force by time, okay? Notice that this is milliseconds, so this is 5 times 10 to the minus 3 seconds, right? Okay. So what I did was I just sort of read the graph, okay? And I just took 5 little things. I divided it up and I said, okay, I'm going to read that little point right there. And I got that was like 1125 or something like that. And then I used that as sort of the average force for this amount of time, right? It's actually maybe a little high, but that's okay. Then I used this point right there. I read that off. I got 1675 or something for that, right? Maybe I did it wrong. Okay, and that's going to, so I just basically divided it into this, right? And then I did this, right? Then I did this. Then I did this, and I found the area. So the impulse is the area under. So I just made these little columns, and I read what this was. So for example, this was 2150, right? Is what I got for that point right there. This point right here, I'm just using the averages. This is 2075. That point there, I got 1925. This point here, I got 1675. And then this one, I got 1125. Okay. And I just assumed that for example, that the area underneath this, right, was the same as the area under the graph. I said for this guy, this area here was the area, same as the area under the graph, right? For this guy here, that's the area under the graph is this, and this is pretty close, right? I mean, here it's above, but there it's below, and et cetera, right? Okay, so what I did was I took all those readings, right? So whatever this force was, right? And I said, I'll call this force 1, force 2, force 3, whoops, force 4, and then the force for the 5th second, right? And I just said that for each one of those, it existed for 1 millisecond, right? So force 1 times 1 times 10 to the minus 3rd, plus force 2 times 1 times 10 to the minus 3rd. Right? Those are the widths of these, right? Each one is 1 times 10 to the minus 3rd wide, right? And this is force times time is what I'm doing, right? Plus force 3 times 1 times 10 to the minus 3rd. Plus force 4, et cetera, right? Times each one of these forces times 1 times 10 to the minus 3, right? and add them all up. And I got a number. They got a slightly different number than I did. It might be because of that first thing there. I got 8.95, which is really pretty close when I did that. But I know the answer is supposed to be like close to 9, so there it is. Okay. Anyway, you want to find the area under the graph. Just make it into little things. Obviously, if we divided this up, right? If we divided it up and did smaller things, right? This is what calculus is, right? If we did smaller things and divided up like that and found all these areas, it would get closer to the actual one, right? And of course, as the width of these approaches 0, the actual area approaches the area we calculate approaches the actual area, right? So you could do that. That'd be more accurate. It's a lot more work. Anyway, I think we answered that part D there. Yeah, there we go.